Report and present. Thanks for that. Totally forgot about that. Okay, so hello everyone. Today we have our first committee hosted event. We're doing a paper reading. We will be looking at this specific actor-critic algorithm that combines two big kind of algorithms in reinforcement learning, and we will specifically be looking at the paper related to that. But before we do that, we will give you a overall reinforcement learning overview. We will go over some reinforcement learning applications, talk a little bit about what kind of problems can be solved with reinforcement learning. Then we'll talk a little bit about how you can approach reading the paper that we'll be looking at today more efficiently. And then we will talk a little bit, we'll show some concepts that will be somewhat useful during this period where we'll read the paper. And then we will actually take some time, about an hour, to go ahead and read the paper on our own, after which we will come back and answer some of your questions that you have, and also look at some actor-critic details and the paper details to hopefully answer some of the questions and make things that are not clear more. And with that, we will go to reinforcement learning overview. And Jacob, take it away.
Yeah, so what is reinforcement learning? It's an unsupervised machine learning method in which AI tries to maximize the cumulative future reward that it gets from the environment. So you've probably seen this diagram before. It's a good explanation of just a basic overview of what is happening. So you have the agent or the AI that performs an action in an environment. We'll define that on the next slide, but it performs an action and the environment spits out a new state, environment changes, and it also spits out a reward that the agent then looks at and determines, okay, what's my next action going to be? And so it keeps on doing this, it keeps on getting an action, keeps on receiving that input, and it does this until it finally reaches end goal, like a final determination of a task. And just next slide, please. Yeah, so some key terminology here. I'm going to relate it to a chessboard because it's pretty good at mapping it to one another. So you have the agent, which is the learner, the decision maker, the AI, whatever you want to call it. In the chess scenario, that's you. You're the agent that performs an action. So, and the environment in that case is the chessboard with all the chess pieces. It's the task at hand that the agent is trying to solve. And on the chessboard, the agent performs an action. It does something. It moves its rook over there or moves its pawn over there. So it's the way the agent interacts with the environment. And then you have the state, which is the outcome of performing an action. So you move your rook over here, your environment changes. It creates a new state. And the agent gets that information of like, okay, feel free to bring up any questions. Oh yeah, no, of course, yeah, bring up any questions, stop me if I'm burning through this or anything like that. So yeah, you have the state, and as a result of an action, you also change the state, but you also get this idea of reward. It's the feedback that you get of moving your pawn here or moving your rook over there. What happened as a result? And then finally, you have a policy. It's the decision-making function of the agent. It's what you want to do. Like, it's your plan, like, okay, I'm going to do this. I'm just going to go straight for the king. I'm going to do that. It's the overall idea that the agent expresses of how it wants to solve the task. So next slide, please. So yeah, from a general overview, and then we'll we're going to dive in more deeper into specifics in a bit, but there are two types of reinforcement learning algorithms. There is model-free and then model-based. So model-free means that the agent uses its past experiences to come up with its next action. And model-based means the agent uses a general understanding of the system, of the environment that it's in order to determine its next action. And model, I don't want you to get confused thinking model is like a SVM model or a random forest classifier. Think of it more as like a loose coupling between like a recipe or like a mapping. It's just the idea that it has laid out of like what it should do within the environment. And one way to like sort of see an example of either one is the other picture on the right is that model-based is, say you have like a paper map that tells you how to get from your house to work. You're going to follow that model. It tells you, okay, to solve my problem, which is to get to work, I'm just going to follow this map, go this road, that road. But model-free doesn't have the map in mind, but it has an experience in mind. It's you remembering like, hey, last time I took the highway, I was stuck in traffic at this time. I don't want to do that. I'm going to make another decision. So it's based off of your experiences. Let's see. And next slide, please. All right. So one last thing is just some general concepts. There's plenty more, but some main concepts that you see in reinforcement learning is one of them is exploration versus exploitation. So it's the trade-off between wanting to explore your environment more versus just exploiting what you already know and getting the reward that way. And the reinforcement learning, it expresses this as like a hyperparameter, which is you decide the percentage of exploration or exploitation, like 20% of the time I want to explore or 30% of the time. And it's a trade-off because obviously there's could be better decisions out there, which makes you want to explore more. You know, think of it as when we first discovered the wheel. Right now, we're not driving around on stone tires. You know, like we explored a bit, but at the same time, you know, you want to exploit the technology that you have, and you know, you want to ask like, okay, why don't we just explore the entire space? You know, in a small environment, it makes sense to, or you know, it's entirely feasible if there's only a certain amount of states. But in a large environment, the agent might just be wasting time on resources, exploring parts of the environment that don't even make sense to explore. It's not helping it solve its task. So there are strategies to determine a good mix, and you know, I'm not going to go into the details of them. There's just different strategies that help you determine a good mix of exploration at first, and then as you figure out the environment a little bit more, tapering off and going more towards exploitation of what you already know. And then there is on policy versus off policy. And this one's a little bit tricky to understand. So on policy is its attempts to evaluate or improve the policy that is used to make the decisions. So you're trying to improve upon your policy with the information that your policy gives. And one way to think of it as is you're learning on the job. So when you learn on the job, you have an experience at work, like boss says, don't wear that color tie. Okay, I'm not going to wear that color tie. You learn from your own experiences. Versus off policy is you evaluate or try to update your policy based off of experiences of other agents, off of their experiences. And the equivalent to this would be looking over someone's shoulder to see what they're doing. So, and this idea can spread to, it doesn't have to just be one person's shoulder. It could be like 20 people. You see their experiences and you just get a feel for, okay, how should I do my next step based off of what they say? Like the boss yelled at them for this, therefore I'm not going to do that. So that's the idea of on policy versus off policy.
I have a quick question.
Yeah.
Cool. Can you talk a little bit about what a policy is?
Uh, yeah, so we're going to go into more of like specific policies, but the policy is the decision-making function of the agent. There's a lot of math behind it, but the main idea is what's the agent's next action going to be? Like, is it going to go left? Is it going to go right? And its policy is saying like, I'm choosing to go left because my policy says I have a better feeling for left based off of what I know right now.
Great, thank you.
Mm-hmm. Then the last concept is the Markov decision process. And it's the mathematical framework that we use to model our decisions. As it says here, it's partly random and partly controlled by the agent. And the key concept here is that the Markov decision process satisfies the Markov property that the future is independent of the past given the present. So that basically means that you don't have to necessarily carry your past experiences because they're implicitly captured in your current state where you're currently at. So you can use that information of where you're at right now in order to predict where you want to go or determine what your future is going to be. And we'll go into more about the Markov decision process, but just as a high level, it's the mathematical framework that we use for reinforcement learning. Any questions so far?
Yeah, I had a question.
Mm-hmm.
So exploration versus exploitation, that sounds pretty similar to model free and model based. Are those related, or are these concepts applied to that?
Let's see. So
What's the question on model-based and model-free versus off-policy and all-policy? Did I get straight?
no, I think exploration versus exploitation.
Oh, okay. Let's see. That's a good
Because
question.
trying to optimize decisions based on existing knowledge sounds like model free to me.
Yes.
Yeah. And model based sounds like the first part.
I would say that it's this concept would be somewhat independent. You can generally do exploration with model-based as well. But I wouldn't be so sure about that.
I would imagine it would be more model free because in model based, you're just determining the model as a whole. So you're gonna explore the entire model. Whereas model free, you're not trying to explore the whole model. You're just trying to figure out just enough in order to have an optimal answer to the problem at hand.
Right, given existing knowledge or past experiences.
Yeah.
Okay.
As far as I understand, I think exploration and exploitation is generally kind of, I think it's, as far as I understand, I could be wrong, but it's independent of whether you have a model or not. I think it's more so how much value do you give the previous knowledge you have versus how much are you willing to let the agent explore to get more information from its environment. Anyone have any ideas?
Yeah.
I'm not sure if it's right.
That's a good comment. To work off of that a little bit, it would intuitively it would make more sense to imagine exploration versus exploitation being more relevant to off-policy methods, where you'd imagine, because you're learning from experience, because you can sort of try to learn what happens when you perform such a certain action. But with model-based algorithms, there are actually some model-based algorithms that learn the model. So you can have the hard-coded model that just tells you what will be if you do the action A. But you can also have a learned model that you try to figure out what happens in that state if you do the certain action. And it is where you will also have this question of how much do you want to explore versus how much you want to exploit, because exploration will be essentially prioritizing actions that take you to states where you haven't been before, and exploitation will prioritize picking and getting into those states that you know have greater value.
Okay,
Yeah, but
thank you.
in model-based and not model-based, the question is different, I guess, of exploration and exploitation.
Mm-hmm.
That's a good question.
Okay.
I have a comment to add to that. One example of how you would do exploration versus exploitation in, say, a model-free environment, a model-free model, I suppose. So in a model-free model, you wouldn't have a model of the world. So let's just say it's like a neural network, which directly maps an input to like some action to do. Then in this case, what exploitation would look like was that you just go with the action output that the neural network decides. But if you want to do exploration, then you could say, okay, 20% of the time, we're not going to do what the neural network wants to do. We're just going to choose something random. And that's an example of how you could explore while having a model-free algorithm.
Thanks, Andrew.
I don't know if that clears up anything.
That makes sense.
Okay.
Yeah, thank you.
Okay.
Any other questions so far? If not, we can move on to applications.
Yeah, Brian's next.
All right, so let's reinforce our understanding of reinforcement learning. I think the idea of reinforcement learning pulls from human behavior. And as humans, we often make mistakes in our everyday lives. But by learning from our mistakes or even being punished for them allows us to make better judgments. I think the same learning applies to reinforcement learning. As an agent interacts with its environment, and based on their inputs and actions, the environment rewards or punishes the agent. And here we have a wide variety of applications for reinforcement learning, such as transportation, robotics, automating industry technologies, simulation modeling, or even video games. And here, a visual representation of reinforcement learning is depicted in a game of Snake. In this example, reinforcement drives the snake's learning process. Here, the environment is our game, and the agent is our snake. More specifically, the environment consists of the square borders and the tokens which the snake needs to eat. On the left, the beginning, the snake moves in an unpredictable pattern, and eventually it can either hit the border and lose the game, punishing the snake. And on the right, we have the snake moving in now like a predictable pattern thanks to it constantly updating its states, either being rewarded by the environment for eating the tokens and continuing to play. And next up, please. So now I wanted to have a quick activity with the audience. I want to ask the audience in this example of Atari, what is the agent, the environment, the action, the reward, and the state?
The agent is the paddle.
Yeah, why do you think it's the paddle?
because that's what we have control over for actions.
Yeah. And how would you say the paddle moves by their actions?
I'll let someone else answer.
Well, yeah, the paddle, aka the agent, moves in an x-axis direction. And Gaston says in the comments that the state is where the ball and paddle are. Yes, that is a role in the state as well, but we can also say that the state can be the number of blocks remaining as well. So there are a lot of incorporations of states in this game. And the action we could say could be, yeah, earlier the slider moving in the x-axis. But what can we say the reward is in this case?
Is the reward like when it hits the blocks?
Yeah, the reward is basically when it hits the blocks, but it can also be also when the paddle hits the ball, because if the paddle misses the ball, then the game basically restarts, right? So yeah, so there are a number of things. There are a number of number of rewards and states going on into this game, and that is why in this GIF we see that the ball kind of purposely hits the ball into a corner, enabling it to hit multiple balls like against the walls and the blocks, and that just shows the reinforcement learning of the whole Atari process. Does anyone have any questions?
If no, we can move on.
Hey everyone. So for the discussion, we wanted to also, since we're going to spend some time reading the paper and trying to understand it by ourselves, and then we're going to be telling you about how everything works and try to explain the mathematical foundation, we wanted to also get a little feel of involvement with the audience. And so we prepared the discussion that you see in your screen. And so I'm going to be asking these questions. Feel free to unmute yourself and start replying. Hopefully different people can participate and we can spark some sort of debate, maybe, if different opinions are contrasting each other. So, all right. So now that we have a brief introduction to state, action, and reward, how would you utilize this technique?
I'm a little confused about the question. Could you explain what you mean by utilize?
Well, we've seen a couple of applications, right? Now, what kind of other environments would this be useful in?
Yeah, let's make it a little bit more specific. Let's imagine first try to think what kind of environment you could use this sort of techniques in.
Potentially some kind of self-driving or autonomous car.
Cool. And what would be like state actions, rewards in there?
State action. A state would be like your latitude, longitude values, or your XY coordinate in the world. Your action would be, well, it would be kind of the XY and then your angle at which you're going. And then the reward would be high if you're on the correct path, and very, very low or negative, or perhaps very negative if you hit a pedestrian.
That's a great ideas. Yes.
Good point with thinking of different kinds of reward. We'll have another question regarding that, see how many we can come up with. So is this trial and error simulation similar or analogous to human learning, and why? why do you think this is how humans learn?
Could you repeat that? Sorry, I couldn't hear you.
I can repeat the question. So, yeah, is this trial and error simulation that the reinforcement sort of practices with analogous to human learning, to how we learn since we're babies, and why?
I think it is analogous to human learning because there's sort of two ways that people learn. One is with no knowledge of how to do a task. You sort of just fumble around until you find something that works, and then you just sort of improve that over time, which we can see that the in the Atari example, the agent eventually learned to just kind of get the ball at the top. And then the other scenario is you're given knowledge about a task where the knowledge might not be complete, and then you use that as your starting point, and then you repeat the process from the first example.
Yeah, so I guess your point there for the second part is that memorization is important to remember the previous sort of rewards and states that an agent has come across with, so that it can learn upon those and so memorize.
Yeah, it doesn't necessarily have to memorize. It could also just be, it's given a strategy to start out with instead of just saying explore, you're giving it some knowledge to exploit.
Cool, cool. Yeah, sounds good. Anyone else has anything to add to this?
Yeah, I'll say something. On the other side of the coin, reinforcement learning, the trial and error, is also different from human learning because humans, beyond just trial and error, we can also learn from communicating with each other, like in school. So in this case, it's not, when a teacher is giving a lecture, it's not really trial and error, but it's like conceptual communication, connecting ideas together in our heads, which is another type of learning, which is not what reinforcement learning seems to do.
And what would you say then for that? How would that differ from multi-system reinforcement learning, where different agents interact with each other to learn a different value function?
Like collaborative reinforcement learning? Yeah, so like there are different multi-agent reinforcement learning algorithms, but they all seem to be based on, they're all still rooted in the trial and error reward function, right? So, and when you do have multiple agents learning a policy, one way you could do that is like you share the same policy across different agents, and they're each updating like the same policy. So it's not exactly like communicating a concept to someone through like, say like slides and pictures and diagrams. It's like still rooted in the same trial and error, I guess, base of reinforcement learning. That's an interesting point though.
Yeah, cool. Anyone else?
I kind of had a question off of what Andrew said. Does anyone know if it's possible? I know like knowledge distillation, where you can kind of use domain information and feed it into neural networks, exists, at least in computer vision. Is that the case in reinforcement learning?
You mean like transfer learning?
Yes, kind of like that, yeah.
I'm not sure. Vlad, do you have any thoughts on this?
That's a good question. Actually, I'm not sure that I'm getting the knowledge distillation right. I know that there are some interesting methods, like you could actually make an argument that off-policy techniques sort of, I guess, sort of get in that direction, I guess, because you can have several policies with different parameters, and you can utilize learning of all of them, and they can learn in parallel. And you can use all of those experiences to combine them into a better model. But you can also, there are also other interesting things like imitation learning that can actually directly try to learn from optimal agents' behavior, like learning from humans. and it can sort of like base its learning on that.
Yeah, and maybe I'm not sure. I haven't played much with it, but I believe that in similar environments, not exactly the same, but similar environments, previously learned policies can apply to that and give you a starting point ahead than a blank slate. So that could also somehow relate to transfer learning. And then from the new environment, or perhaps the new responsibilities of the agent in that environment, then it's got a better starting point and it can improve the learning efficiency in the process.
Oh, I see. Okay, cool. So you're saying rather than transferring to different tasks, you can transfer the agent to different environments.
You could try. I mean, the policy is applicable, and once it's perfect, not perfected, but optimized, you could apply that policy in similar environments.
Cool. Thanks, Miguel. Thanks, Vlad.
Yeah. All right. So if anyone has anything else on this one, speak up now because I'm gonna jump into the next one. All right. So I don't know if you're familiar with generative adversarial networks, GANs. They're a hot topic nowadays, but what similarities do you see between actor-critic algorithms? Which, I mean, we still haven't gotten much into it yet, but like let me introduce a little bit. It does compose two different sort of algorithms that improve the learning efficiency from one another by applying techniques simultaneously. So I don't know if you're familiar with this. Perhaps you can say what similarities or differences you can see in this.
You could also just think in general with reinforcement learning concepts, and if there are any anything similar to that, or maybe you could use from other fields of machine.
I think the critic part of the actor-critic is kind of similar to the discriminator part of the GANs in this. Oh, sorry, this is a big block. In the sense that the discriminator is judging the output of the generator, and then it's very similar to the critic judging the output of the actor, which is essentially just a change of state. So in that way, they're the same, but I think it's a bit different because the actor doesn't really end up generating stuff in a discrete sense like the generator of a GAN will, where like a GAN would be more like you could teach it to create like a deep fake or a really real photorealistic image of like some fake celebrity or something, whereas in reinforcement learning, the learning doesn't really have to stop. It can kind of just keep going until some arbitrary breaking point, or I'm sure it could even learn as it's being demoed. Correct me if I'm wrong, but I think that's the case.
Yeah, I liked how you started with comparing the discriminator to the critic, and I think that's the right way that I thought of directing this question. So that's right. I think I see that sort of similarity too. It's not explicitly the same, but it does have some sort of similarity in it. Anyone wants to add something? Or I know this is kind of an ambiguous question and kind of like jumping ahead of what we're going to be discussing today, but if anyone else wants to contribute, feel free.
Oh, I don't know enough about actor-critic algorithms, but I wonder if there's also kind of this mini-max game that you play in actor-critic algorithms. That's just kind of my only insight.
It is used in the critic part, but it's not exactly what we're doing to big decisions. It's a great question, yes. But the ideas from the techniques that you use in minimax game apply that, because you use the value. we'll get into it.
All right. So next question. I liked how Gaurav sort of devised already kind of an answer to this question, but what kind of different reinforcements or rewards can you think of for a system? Obviously, we've discussed positive rewards, where if you perform according to the expectation, you get a positive reward. But what kind of other scenarios would imply different kinds of rewards? I'll pick someone. All right, let's see who's been quiet. Pushpal?
Hi, sorry. I was actually replying to Andrew in the chat, so I was busy. I didn't hear your question.
Yeah, basically it's the fourth one. What kind of reinforcements or rewards, like we're calling it rewards in the Markov's decision process, can you come up with? We mentioned positive rewards as reinforcing an action according to expectation, or to sort of positive expectation. But what kind of other reinforcements or rewards do you think might be applicable for different systems?
Well, so if we have positive rewards, then there can be negative rewards for punishments. Yeah. I don't know how to explain that. It's pretty self-explanatory. You can punish the, what is it, algorithm? Yeah. So that it knows not to do that again.
Yeah. So if what Gaurav said earlier, if someone you're teaching reinforcement learning to a car and the car runs over a pedestrian, then that's a very strong negative reinforcement policy. Or
right, you might put in jail.
Yeah. Anything?
If you don't mind me asking a question, what happens in the case of a sort of neutral action? Like if we were to think of the car, let's say that stopping at a stoplight would be like something that is positively rewarded and running over somebody is negatively rewarded. What about something that's sort of neutral? So it's just going straight, or just there's nothing around it, so it doesn't really need to change that much.
I mean, probably in that case, I mean, if you're supposed to stop at a stop sign, I don't know, because I feel like that case, it sort of applies to positive reward. It's expecting what you should be doing. It is, so.
I guess a better example is, let's say your agent is trying to find like some item or whatever, and it just takes a step. And after it takes a step, it still has like no idea where the item actually is. It needs to keep exploring. How would something like that get translated? Like I know it would be implementation dependent.
Yeah, I think it depends on the application itself, but generally, I think that's you give a reward. I don't think you give a very positive reward. You definitely don't give it a negative reward. I think it pretty much depends on application, but a neutral reward would be like 1 or 2, but whereas positive would be like 1,000, negative would be like negative 1,000. But in the lane example, if you're not in the lane, then you get a slight negative reward to be like, no, get back in the lane. That's my insight.
Yeah, also it goes by like probability. So like we'll touch on like a transition matrix from a state to another state. So let's just say like if the actor already done that action previously, and that like even like maybe they can gauge like the latitude or longitude of that area or something, where it's like a very small incremental change, or like on the probability of it leading to a real positive reward, like a bigger positive reward. So it won't be necessarily on the reward itself. It'll be like maybe like leading up to that system of it.
It's a great discussion on rewards. It's very important to, and it's hard to come up with actually good rewards for environments. It's hard enough to learn them, but to come up with them is also a great challenge.
All right, so we have a final scenario. I feel like some people, depending on the committee you are, might be more inclined to jump into your field for this one. But so imagine you're teaching a robotic hand how to solve a Rubik's cube. What kind of systems is that sort of application going to need? And by systems mean like algorithms or applications.
I think you're gonna need like a hardware system to be able to actually detect in some way which state the Rubik's Cube is in.
Maybe employ some sort of computer vision there to detect the state of the cube at a certain point. I don't know. Computer vision committee, what do you think?
Yeah, I think you can look at the pixels, right? That's on the screen. It's gonna be very interesting because you're gonna also have to be able to tell, depending on like which angle the Rubik's Cube is at, right? Which sides are gonna be like the top and bottom, side to side. So like, are you gonna have the Rubik's Cube set at the same angle and position every time? Or is it, like, do you have to have the robot consider, oh, this might be a different position, so you'd have to be able to detect where the points are. And then I guess you're gonna have to like see every single, you're gonna, like, if it's gonna be a brand new cube every time, you're gonna have to know like every single point like of the Rubik's Cube. Or maybe you can twist it and then like test it around, like twist it around, and then you can then see all the possible, like what the actual state is after you like move it around a little bit.
So like scan each side every time you move.
Yeah, like maybe, like it would like twist it around top to bottom, side to side, so that it could detect each side instead of having to have like 8 cameras to check for every single side.
Right.
There are certain points that are sort of you can infer, like these centers, the colors on the centers are opposite, or they're sort of, they stay the same in the center, depending on if you see, I don't know, white on one top, then for sure the opposite, it's gonna be red. I'm not sure if that's how it actually is, but those don't change, so that can also simplify some of the things. It is true that for other parts is more complicated, and we would have to take a look into what the position of the tiles are in each specific moment. What kind of other stuff can you think of? Not just computer vision, but other committees as well.
I think like a general algorithms. Sorry, go ahead.
No, go ahead.
I think there are like general algorithms in solving a Rubik's Cube that you can utilize, like that techniques that humans would use, and then try to see if that's something like a robotic hand could do. So I don't think that's necessarily machine learning related, but it is like an algorithm that you would use. Like there's systematic algorithms that you would use that could solve the Rubik's Cube from any state.
Yeah, there's like an optimal policy, let's say, or an optimal sort of trajectory set of movements to complete the cube given a certain state. And that is true. It's probably given by some sort of algorithm, human inferred, but that could be sort of analogous to other machine learning stuff, sort of a value function, an objective value function that you want to minimize, right?
I think you could use that algorithm that you talked about as like a heuristic or starting point for the hand's policy for solving the cube, or you could have some sort of indicator as to when the heuristic will be the most effective, and if that point is reached, then you just switch over to the algorithm instead of the reinforcement learning. Just do that. Sort of force it to take the path of the algorithm, unless it magically learns something more efficient. because I mean I don't know any Rubik's cube solving algorithms, but I assume given like a cube in a random state, you just kind of fiddle until you get to some breakpoint, and then from that breakpoint it just follows an algorithm, and then you have like a number of steps you do.
Yeah, yeah. What about moving the hands? How would you approach that? What kind of field would you think that belongs to?
Wouldn't that be robotics?
Yeah,
Related?
yeah. And what kind of like algorithms would push those sort of robotics? Because he has to sense, right?
Yeah, so it has to sense like the weight and different parameters of the Rubik's Cube as well.
Totally, totally. I think reinforcement learning is good for that. I've seen some examples where they teach robotic hands to solve Rubik's cubes with one hand only. Yeah. Any other sort of possible algorithms that a system like this might need?
Might want to consider, yeah, like the torsion, like twisting, how much twisting force you would need to move move a specific side, a specific amount. And that might depend actually, because it's so precise of a robot, right, on like how the Rubik's Cube responds to it. Because some Rubik's Cubes are have more resistance than others, so you'd have to take that into account as well.
I'm not sure, but like yesterday I saw a video that had like it wasn't an algorithm based thing, but like it had 4 steps. I don't remember the steps, but probably how we can teach the machine is that we can have the robot's right hand move, like the right hand would be fixed and it would just move clockwise and counterclockwise. Like it would rotate the cube counterclockwise and clockwise horizontally, and the left hand could move it vertically. Like there were 4 steps. The right hand just moved vertically, clockwise and anti-clockwise, and the left hand moved horizontally, clockwise and anti-clockwise. And like after those 4 steps, the algorithm can check if the cube is solved or not. If not, then it could repeat itself again, the 4 steps. So like probably that is one of the techniques how this could be solved, but I don't know how to teach.
Totally agreed on that. All right, anyone else, or we jump into I don't know if it's rating now, but I think we're gonna introduce the three pass technique. But yeah, I don't know. Anyone else has anything to add to this topic?
I just had a general comment on that. It sounds like there's a lot of stuff you can do to solve the Rubik's Cube, and a lot of it is very specific. So it's like really depends on the Rubik's Cube having a certain, I guess, structure, and with there being a certain number of rules, let's say. And so the solutions for them are sort of like, it's hard to make that general. So perhaps in some ways, machine learning algorithms can help us to make that more general, but that's just
so quick question, does anyone actually know how to solve the Rubik's Cube here?
I used to. I don't know if I remember anymore.
Okay, so I do. And it's funny that you're talking about algorithms, because like the method for like a human to solve a Rubik's Cube is they follow what they call specific algorithms, which so there's a language that determines which side of the Rubik's Cube moves and how you move it. They're clockwise or counterclockwise. And you treat the cube as having a front and a back, and a top and a bottom, and a left and a right. So by orienting certain combinations of either, turn left clockwise or turn left counterclockwise or something, you follow those moves, and then you'll solve the cube. And to solve the cube, you have a specific order of air quotes algorithms that you would use or humans would use, and then you will be able to solve the cube each time. And each of these algorithms, they have a known way of permuting the cube. So if you are able to train your model to know each of these algorithms, they could figure out the exact order to move each square color to the correct places, I would suppose.
Totally. Yeah, I remember I used to some of those algorithms that you mentioned. It's just like the way I solved the Rubik's cube when I was younger. It was just try that same move every time and wait for it to work.
Sure.
Yeah.
Sounds great. Let's see. We are at 4:56. Do you guys want to take a break, 5-minute break, or are you good? Can like raise your hand if you.
I think a 5-minute break would be much appreciated for anyone who needs to use the bathroom.
Absolutely. Let's do that then. We will return at.
So just to clarify, after the break, we're gonna be reading the paper on our own. Is that it?
We will introduce some concepts that will be helpful for you. Then I will surely tell you about some useful method that we can use to that. And yeah, we will spend some time, not an hour, probably about half an hour to read it, and then return.
Right. So we're back at 5:02.
Yes.
Cool.
Something like that. It's 5:01 for me, but
By the way, Vlad, I just wanted to mention that the meeting is going really well so far. I can tell that you guys prepared a lot, and the slides are really good, and everything you're doing is great. So
I love the discussion questions, I'm gonna be honest.
yeah, awesome.
thanks, Andrew. I think everyone did a very good job.
I'm glad we have something to take. We should add the discussion questions to future paper readings as well. Great leader, King Vlad. I like that.
It looks like it's 5:02, and we can continue. Let me resume my sharing. Okay. So now, Sadine, why don't you tell us a little bit, prepare us a little bit to what's to come in paper reading, so that we are all a little bit more prepared for it. Let's see if Sadine is back from the break, actually.
All right, yeah. Are you guys hearing me now? Okay. Well, now we're gonna hone into more on what actor-critic actually is. So first, you want to really know what actor-only methods are and actor-critic-only methods are. We kind of address this with like the general applications of RL. And a critic only is usually value-based, where you try to find like the optimal value function between an action and the value or like the reward. And the higher the value, the better the action. One of the most important ones, if you might have heard, is Q learning, and that's usually around critic-only methods. And then for actor, it's usually mainly on like policy-based, where the policy algorithms are to like reinforce the optimal policy without using like a Q value as like a middleman. And then when you think about like these two separate methods, you would think, yeah, why not just merge them, right? Like use Q values, which I'll extend on later, and then onto a policy. So the main thing is that actor critics aim to take advantage of all the benefits of both the value-based and policy-based, without also while minimizing any of the drawbacks that either one has. So the main thing is, like you can see from the diagram, where it is kind of what Jacob was going off on the diagram, where you have environment and the policy. You just like also incorporate the critic components onto it, where there's like a value function, and the critic tells the actor how good the action is, and then updates the policy parameters for in the direction of like performance improvement for the actor. And so overall, the critic is just an approximation architecture that learns a value function, and then updates the policy. So overall, critic-only policies have better convergence when it comes to like gradient descent. So finding the optimal thing compared to actor-only, because given actor-only is like more sparse, and actor-critic methods, or the merge of these two methods, overall it does have better convergence compared to critic-only ones. All right, next slide, please. So the main thing about this paper is that section 2 has a lot of notation and math that is not fully applied to actor-critic algorithm itself, but then it has a good background on the notation and kind of justifies of the author's approach to coming up to using actor-critic components in a single model. So mainly section 2 is stating a formula of the gradient of the average cost in a Markov decision process, and then providing a new interpretation. So like rearranging some parts of the previous algorithm of actor only to incorporate critic only parameters. And a good suggestion would be that to first read section 3's first 3 paragraphs that kind of summarizes section 2, so you don't get too stuck up on like the heavy notation or the math that comes up for that algorithm. And the main thing is that for this paper is that we view actor-critic algorithms as like a stochastic gradient algorithms on the parameter of the actor. Like you can see like the actor is in the outside, and that's like the main pull to the environment, right? And the critic is just its own like separate value function. So the main parameter of the actor is like break up into like feature vectors, and the job of the critic is like to get the approximation of the projection on the subspace, which I'll explain how the authors made to that conclusion of reducing the dimensions, but still getting the optimal like way of converging to the best action. So yeah. some general concepts here is that we are working on a finite state space. So you can see like the gridded boxes here for like I said, like a robot vacuum to only go on to those finite number of squares. And a finite action space where like just say the robot can go diagonal in this instance, it can go forward and backward. And also like randomized stationary policies in terms of the vector of the feature vectors. So like, yeah. The main thing is that the authors are using Markov chains as like a primary like component to incorporate critic-only methods onto actor-only methods. So Markov chains are consist of the 3 different elements: the state space, which I already mentioned before, the transition operator, so like the probability of moving one state to another, so like one square to another square, and then the initial conditional distribution, which is kind of like the probability of the vacuum starting from anywhere, so from any square. And usually if the state space of the Markov chain is finite or has like no distinct values or distinct squares, then it is like time dependent, or it can go along with time pretty well. And you can also gauge time as a parameter of itself. And then with that, you can make like, because it is in a finite state, you can have a better like initial like number of elements of the matrices, where you can go from I of columns and I of rows. And yeah, so overall, the notation that the paper uses is like the sequence of states, which is denoted by x, xn, so x0 all the way to xn, and state pairs of u, which are of the actions. And so they take the pair of x and u's, and then they make Markov chain, like you can see the visualization of that from B and A, and respectively. You can also go to the link here. I'll put, if you guys still not familiar with Markov chains, it has a pretty good diagram and has like the more of a transition matrix visualization that you guys can see of why the authors chose this, and also like why like reinforcement learning in general relies on Markov chains. All right, next slide. Okay, I won't go too much into notation. Like you guys will probably look at the equation and read it, and then like a good suggestion would also be that to maybe like write down like a table of all the notation that you want to keep on remembering when you're going through the equations, so you can just update whenever like you kind of forgot what that notation is. So one of the things is that the 1 or the lambda for the first one is like a average cost function, and V is like the expected cost function. So the thing is like V is like used as a disadvantage of state X. So, and X, I already mentioned before, is like the state. And the main thing is that like the reason, so the main approach of what they were trying to do is minimizing the actions to have the most optimal actions over the feature vectors, right? So this is pretty much the Poisson equation for that. And there are other parts of it where like G, I didn't make a notation of that, or like let's say G of XU. That is also another cost function of like the probability distribution. It's like the transition matrix of the Markov chain. And yeah, like I'm just throwing it out there right now, so later on you guys can the general haze of it will clear up as you read the paper. All right. So primarily in section 2, when you're trying to gloss over it, they're trying to take from the left equation and then using inner product to change up the values and the sums to make an interpretation of the algorithm that incorporates Markov chains and critic-only components onto an actor parameters. So that's mainly what we're trying to do here. And so like they're going on like they're going over like a certain renewal period of the Markov chain of X and U pairs, and under that specific policy, like a randomized policy, and then doing whatever estimations onto it. Yeah. And then so like the finally, like the whole thing of why this happens is that to overall reduce the dimensionality of like the action vectors to get the Q value as low as possible among whatever a very high dimensional space. So let's just say you have a lot of like states that you can go to, and you only have a finite number of actions, right? So like it's trying to accommodate that with like a min onto it. And yeah.
Thanks, Adine. So that's generally on what's to come in the paper. So you can look up to that and sort of generate the questions easily. Now I will tell you a little bit about the strategy that you can use to approach reading the paper more efficiently. We will not be able to utilize all of it today, but rather the first two parts of it. So this is called a three-pass approach, and generally I refer to these three passes as overview, read, and re-implement. We will be focusing on the first two, as we will have time to do that, and not the third one. So essentially, in the overview part, you will first read the title, abstract, and introduction. You will read sections, headings, conclusion, references, in order to get a general understanding. What's the paper about? What's the category of the paper? What's the context of that? So in the end of that, you will know general idea, you will know what's the relevant research. And this phase should take you a little bit, about like five minutes, 5 to 10 minutes. Now, the next part is where you would do most of the reading. This for today is you will look at the graphs, diagrams, and just go over all the text on all the body of the paper. The outcomes of that is you should be able to somewhat summarize the general idea, summarize the points that the authors are trying to make, and the most interesting for us, especially today, is to identify unknowns and come up with questions that you don't understand about the paper or reinforcement learning. Authors of papers say that it should take you about 1 hour, which we will not have time today to do all of that, but generally it will take most of your time today. Finally, for the re-implement, that's an advanced stage that you would want to use when you're reading especially a computer science paper. The purpose of that is where you would really go into details. You'll understand everything that is used in the paper, every other referred research. You'll be able to derive math that is used in the research, and essentially you'll be able to recreate the paper using the methodology that authors used. And authors say that should roughly take you about 6 hours, though that will probably more depend on the paper. Again, we're not going over that today. So for the paper reading, what I want to encourage you to do is to look at the couple of questions. Actually, I've updated the slides as we were speaking, and we have a link to the paper, and two questions to you. Like, what during this paper reading, try to sort of figure out what's actor-based and critic-based algorithms, methods, and how it is that this paper is combining them. How does that work? And with that, let's take half an hour. We will return at in half an hour. That's 5 45, not exactly half an hour, a little bit less, but try to come up with questions, try to answer specifically these two questions. Don't hesitate to research, do additional research and look for additional methods and come up with questions. Any questions before we go into that?
I'm wondering if it might be easier to read if like you share screen of the paper and we can all read like section by section or ask questions per section. That's just a recommendation. I don't know what you guys think.
We could do that, although I would say it would probably be easier if people can sort of jump into the different parts of the paper as they find needed. So
sounds good.
Okay, then I will see you in about 27 minutes. Okay, how's everyone doing? It's very math heavy.
Kind of confused.
I'm still reading.
Okay, so let's see. Let's try to figure out, try to answer the questions that we have so far, because we will have little time remaining, and we'll need to focus on stuff that we can answer, basically. First, were you guys able to answer the questions on?
Hey, I don't know if it's just me, but I can't actually see what you're sharing. It just says that Vlad has started screen sharing. I don't actually see. Oh,
Yeah.
there we go.
Thanks. Yeah. I just resumed. Yeah. Then we get a chance to answer these questions. I saw some answers in the chat, actually. Anyone else?
I think the paper said that the actor-based methods are just sort of acting based off of a policy that can change over time. And then the downside is that it doesn't really learn in the sense that past attempts don't really matter. It's just the current policy that matters. So whatever you did like 10 iterations ago isn't really considered. And then the critic based method is you just sort of, like, it's not a policy based one. I don't quite remember what critic based version was, but I'm pretty confident that the actor based one is based off of a policy.
Cool.
The critic is based off values.
You want to elaborate on that, or somebody wants to elaborate on that? Anyone?
Well, I see in the chat that Vlad, you were going to touch on the TD algorithm once we're back. So do you want to expand on that? Because I'm still kind of confused on that.
Sure, yes. They refer to that. They don't even, I don't think they even explain the abbreviation of TD. They just sort of, hey, we're using TD. Hello. So TD algorithms are, in general, in reinforcement learning theory, it is the general idea of TD algorithms that you can look at value returns as, let's see, you can have, I think, some introduction to critic-based methods is required before we go to that. So the general idea of critic-based methods would be that you would have some sort of value function approximation that will tell you what's the approximate value of being in a certain state, and or a certain value of being in a certain state and taking an action. And usually one way that you can do this is you can try to learn what will be the actual value of this state and every state that is following the state if we are executing under the certain policy. So it is one way that you can do this. TD algorithm and TD methods say that you can actually have a value function that will approximate just what's the output of the next state. So what would be the output of next state? And sort of doesn't matter what follows. At least that's my understanding so far. And the advantage of that method is that you don't need to end until the end of the episode if you want to update your value. You can just, well, you see, I've taken this action in this state, and I can immediately update my value function. I can immediately say, okay, that's what happened. That's the difference of what happened, and I don't necessarily care about what happens later. So you could imagine one example would be where it might be useful is they provide, for example, you're driving to work, right? And you try to approximate what time it will take you. And if you're using a sort of default approach where you just use one value function, you will end up approximating about the same arrival time, yes. Even if you get, for example, in I guess no, you will estimate different time, but if you get, for example, in a traffic jam, then you will need to actually wait when you actually get to your job to say that, well, I was actually wrong, that this is how much time it should have taken. But if you're using TD algorithms, then you can more reliably, you can update your value right when you are at the jam, for example. And you can say, okay, doesn't, based on what you're observing right now, doesn't look like we can get there. And essentially it allows you to make use of updates more often in the episode. And specifically what they refer to in the paper, they also refer to TD lambda, is that it is something in between of, let's say, the default value estimating function, where you would just take all the rewards and try to use all the rewards to update your value function, and it is something in the middle of actually just using the next state updates, if that makes sense. So yeah, that will be my understanding. Did anyone else get a chance to look at temporal difference? I know that some of you got a chance to look at fallibility traces, and that's sort of like thing that is in between of that standard way you would update and the TD methods. That's actually that's considered to be a TD method. So anyone has anything to add or correct me on something?
I don't mean to, I'm not correcting you. I think I'm just trying to reinforce my understanding. It seems that the different methods of TD are how many state action pairs you use to update your model. Is that kind of correct?
Yeah, this is what it sounds to me like, yes. So,
cool.
Okay. Yeah, and then I want to get a understanding of how exactly is that they combine these TD methods. Why are they relevant in this? Oh, that's cool too. Let's see. So in that case, I can, in general, just summarize what's the idea of using the Actor-Critic here. So in general, you would want to, the main idea of using Actor-Critic would be to use your current understanding of what's the value of being in that state to update your policy. So usually in let's say actor-based methods, you would use current actor's gradient, and you would scale it with the reward it actually got, and this is how you would update the actor. But with Actor-Critic, you can actually boost that with your own understanding of how you're doing. That's where the critic comes in. And specifically in this paper, they are actually arguing that you can not only do that, not only you can bootstrap the actor's learning using these imagined values, not imagined, but approximated values. You can also, it also benefits if you use shared parameters for actor and critic. So that's one of the big ideas, I guess, in Actor-Critic in general. Let's see, what other questions did you guys have on that paper? I know that's there's probably a lot of stuff and real concepts in general. Anything specific or anything that's in the paper that seemed really confusing?
Yeah, they mentioned that it's ideal for the actor-critic combination algorithm that they described, that in order for the critic to grow well, the actor has to grow slow, and I was kind of not really sure why that was the case. I'm not sure if I missed something or I just didn't understand it.
That's a great question. I am not sure that I really have an answer to that, though. I'm not sure about that. So the actor needs to grow slow.
Where does it say that in the paper, Gaston? Could you point us?
On page 4 at the end of the second paragraph.
Let's look at it.
So it says, we note some minor differences, and it's in the last sentence is where they bring it up. Not 100% sure. Yeah.
What was it?
You just passed the page.
Okay.
It's the next page. Yeah, this one. It's the second paragraph.
Mm-hmm.
It looks like references 6
Here.
and 2.
Yeah. Yeah, let's go and see what's essentially they might be referring to some observations. To STEM skills.
Well, then I'll just assume that the reason is that there is some potential problem if the actor updates too fast, or conversely, the critic is updating too slow.
Maybe it can't catch up efficiently.
I'm not sure. Well, maybe it has to do with the fact that it's that they only care about the projection. So if you move too fast, then the data that's getting sent to the critic has much of an information loss.
Right. You could imagine that values of taking action in certain states would depend on your policy, right? So perhaps you could save if you're suddenly starting to act differently, then your values are no longer accurate, or make some sort of argument like that. It's a good question. We're coming to the end of the paper reading. I think there's a lot of questions that would be interesting to answer. Though I'm generally glad that we were able to set time to do the general discussion of reinforcement learning too. Guraf, you had something that you wanted to announce, I believe.
Yeah, thank you for the great presentation, Vlad, and the whole RL committee. You guys did a great job today. So thank you for sharing this awesome paper with all of us. I made this announcement in general and announcements, but I also wanted to have one last pitch. We are hosting our climate change panel tomorrow. We're very excited. Over 190 people have signed up. So we're almost closing on my goal of 200 attendees. So if you can make it tomorrow, please sign up and share the link with your friends. It'd be much appreciated. I know most of you are signed up in this call right now, so sharing with your friends would be great. Appreciate it, and I'll see all of you tomorrow. Thank you.
Thanks, everyone. Have a great one.
Thank you. Bye.
Thank you.
Thanks.